Hey guys, in today's video, I'm going to talk to you about QuickSort and their efficiency against a very popular sorting algorithm, which is the BubbleSort. First, I'm going to tell you about how a QuickSort works. In my rendition of the QuickSort, I'm using a divide and conquer strategy in tackling the array. In this case, I'm going to use the last element in the array as a pivot while keeping the items on the left side of the pivot to be smaller and the items on the right side of the pivot would be larger. We have 3 pointers. The first two is the pointer that we declared as I and j, and the last one is a pointer that we declared as pivot. We will put the I pointer to the -1 position in the array, and we put the j pointer to the 0 position in the array. We want to check if the j pointer is smaller than the pivot. If yes, then increment the I pointer and swap the element between the j and the I. In here, the j pointer is actually smaller than the pivot. That's why we're going to increment the I to the 0th position. However, because the j is still in the 0th position, there will be no change made onto the array. And then we move the j to another position in the array incrementally until it reaches pivot -1. In here, during the first, second, and third position, we will not change anything because the condition where j is smaller than pivot is not met. In the fourth position, however, the condition where j is lesser than pivot is met. Hence, we would increment the I pointer and change the value between the I pointer and the j pointer. In the fifth position, the condition is also true. Therefore, we would increment the I pointer and change the value between the I pointer and the j pointer. And now, after the j pointer reached the position where pivot -1, we need to change the value of I plus 1 with the value of pivot. After this operation, we would successfully divided the array into 2 smaller subdivisions, which is the lower partition and the higher partition. Now, we can do the same operation to both the lower partition and the higher partition. And now, we will translate the algorithm into a working program. In this video, I'm going to demonstrate it using the C++ programming language. I already created the programs beforehand, and the source code that are used in this program can be viewed in my GitHub repository, which is available on the description box below. In my rendition of the program, I created 4 functions, which is the swapper, partition, quicksort, and showArray. The swapper is created to swap between the j and the I pointer. The partition function is created to sort the array that already divided by the quicksort function. And the showArray is a function to display the array to the user after the process of sorting. In my program, I'm also incorporating a chrono header to count the running time that are required by the quicksort. We're going to need this header to be able to determine who's going to be faster in sorting 10,000 numbers. And then, I also have an optimized BubbleSort program, which is actually a very practical for small amount of number sorting. But this program is a very horrible in sorting a very large amount of number. I'm going to use a website called Number Generator to generate 10,000 random numbers starting from 0 to 10,000. As you can see, the QuickSort only took 33,307 microseconds to sort the 10,000 numbers. However, in the BubbleSort program, it took 622,520 microseconds to be able to sort the numbers. But it could have been just the QuickSort that got lucky. That's why we're going to try it again using different random number to sort this time. Now, I think that the QuickSort got very lucky this time. The definition of luck here is that the pivot can divide a large amount of array directly in the middle. That's why this time the QuickSort only took 6,046 microseconds to do the sorting. However, the result of the BubbleSort is almost the same with our last try. BubbleSort took 620,195 microseconds to sort the array. We're going to try it out again to make sure that the QuickSort is really more efficient than the BubbleSort. So, in this last try, the QuickSort algorithm is able to sort the array in just 20,367 microseconds, while the BubbleSort took 608,788 microseconds. So, I guess we have a clear winner here, and that winner is the QuickSort algorithm. So, that's all for this video. I hope you enjoy it and see you in the next video. Bye bye.